Okay, section 7.5, the Dirac delta function. Okay, so a unit impulse, okay. Mechanical systems are often acted on by an external force or electromotive force in an electrical circuit of large magnitude that acts only for a very short period of time. Okay, so a vibrating airplane wing could be struck by lightning. A mass on a spring could be given a sharp blow by a ball-peen hammer. Or a ball could be sent soaring when struck violently by some kind of club. Okay, so of course, you know, we've all had like jolts in the electrical system, right? So, but they last just an instant, right? Well, we need a function to model this kind of phenomenon. And there is a function called the, hold on here, right. It's this function, and I don't want to get too heavy into it, but this is an impulse function called, well, it's an impulse function. So look at what they have here. This delta function is equal to 0 when t is less than t sub 0 minus an a value. It equals 1 over 2a. It has a height, it has a value, when t is between t sub 0 minus a and t sub 0 plus a. Okay, and a is some unit of time. Okay, and then it equals 0 when t is greater than or equal to t sub 0 plus a. Okay, so graphically, if we want to see what this looks like, this interesting function, okay, this is what the unit impulse function looks like. Okay, right here, hold on. Let me get it up a little bit here. Yeah. This is a unit impulse function that it's a piecewise function, as you can see. And when time is between between an interval of t sub 0 minus a and t sub 0 plus a, then this impulse function takes on a value. It's not equal to 0. So the width of this impulse function is going to equal 2a, and the height is 1 over 2a. Well, what's 1 divided by, if we think about like area under that function, what's the area going to equal? The height is 1 over 2a, and the 2a is the width. That's right, Antonio. Very good. 1, because 1 over 2a times 2a equals 1. Okay. So you see, you know, if we're consistent and always require that where the impulse occurs, that the height of the impulse is 1 over 2a and the width of the impulse is over a time interval 2a seconds or whatever long, then what would happen if we were to decrease a? Okay, well, here is the behavior of this impulse function as a approaches 0. So as a approaches 0, you're decreasing the interval, the time interval, about that t sub 0 value, that specific time value. So like you know, we're trying to model this, say, jolt of electricity that occurs almost instantaneously or over a very short time interval. Well, if we let a approach 0, if we let a get smaller and smaller, you're going to see basically a impulse interval, or an impulse that resembles a spike. Okay, it starts to resemble a spike. Okay, and what would happen, you think, to that spike as if a were to go to infinity? What's the height of that spike going to equal? what would the height of that spike equal? I mean, what?
You said if E goes to infinity?
That's correct. That's correct.
Okay, that's
Because
zero.
the width does go to 0, Mark. The time interval gets less and less, but then because the width of the time interval and the height of the spike have to equal 1, if you decrease your time interval, then you got to increase the height. So that's right, Michael. That's right. And so then this gives us the concept of what a Dirac delta function is. Okay, and there it is, right there. So the Dirac delta function, okay, is a function that it's to model this unit impulse. And actually, hold on, I wanted to. This is really what I wanted. I mean, that's just a notation of what Dirac delta function is, but in terms of the behavior we just saw, okay, this is absolutely true. This is absolutely true. The Dirac delta function will equal infinity when at time t equals 0, and it equals 0 elsewhere. And further, that again, that models. We saw a picture of this. We just talked about this, and also the integral of the Dirac delta function from 0 to infinity equals 1. So both of these, both conditions 1 and 2, 1 and, hold on, let me make sure it shows nicely. Both conditions 1 and 2 are conditions then that we use to model the unit impulse function, and it makes absolutely good sense based on the how we derived it. So naturally, what we want to do is, okay, we have this Dirac delta function. Okay, we have this Dirac delta function, and it's going to be a driving force, another driving force that we could encounter in our differential equation. So what's the Laplace transform of the Dirac delta function? Well, they actually derive it here. Okay, and I don't want to get too, I mean, the proof is below. I'll let you look at that. But the Laplace transform of the Dirac delta function is equal to e to the negative s times t to the 0 power. Okay, I guess we can, well, I don't want to get too caught up into the details, but the proof's below. The proof's below. Let's see here if there's, the proof relies on the fact, that the Dirac delta function can be written as the difference of two unit step functions, and then it goes from there. But let's not get caught up in too many heavy details. Let's go right to the, I mean, it'll be intuitive, that Laplace transform over time. I mean, what I mean is in time here as you practice it. Let me just see here. Okay, so let's get right to an example here. Okay. Okay, so two initial value problems. So here, okay, you have a second order differential equation where the driving force on the right is equal to 4 times that Dirac delta function. Okay, and they mention here, okay, and then the initial condition then on this second order differential equation, initially A, y of 0 equals 1 and y prime of 0 equals 0. That's for A. And then B, they have y of 0 equals 0 and y prime of 0 equals 0. And they mention here that the two initial value problems could serve as models for describing the motion of a mass on a spring moving in a medium which damping is negligible. Okay, why would damping be negligible, class, in example 1? They're making a comment. They're making a comment here, and they're saying that damping is negligible. How do we know that? Based on the differential equation. Well, hint, think about auxiliary equation. What's the auxiliary equation for this, for that? So the homogeneous differential equation is y double prime plus y equals 0. Okay, what's the auxiliary equation for that? Well, that's right. Okay, Matthew. So I was thinking, m squared plus 1 equals 0, so m equals plus or minus I, and so the what do you call it? The homogeneous solution is just a linear combination of a cosine and a sine function. But also, Matthew made a good point. In the differential equation here, there's no y prime term, so the dampening coefficient is a multiple of the first derivative term, because dampening would increase with velocity, right? It's like rubbing, sliding on a carpet. You're gonna get the carpet's gonna oppose you more the faster you're sliding on the carpet. So yeah, excellent. So okay, now at t equals 2 pi, the mass is given a sharp blow. The mass is given a sharp blow at 2 pi because the Dirac delta function is t minus 2 pi. Okay, and they also note here that in A, the mass is released from 1 unit below the equilibrium position, and then in B, the mass is at rest in the equilibrium position. Okay, all stuff that you know pretty well. So what we want to do is we want to solve the differential equation. So we're going to take the Laplace transform of both sides of the differential equation. Okay, and if you take the Laplace transforms, obviously they leave out steps. On the final exam, I'm going to want to see steps, right? But if you take the Laplace transform of that differential equation, you're going to get s squared times y of s minus 1s plus y of s equals 4 times e to the negative 2 pi s. The 4 times e to the negative 2 pi s, that Laplace transform just comes from the what the Laplace transform is for the Dirac delta function. Okay, so let me go back down here. So obviously t sub 0 is 2 pi. Okay, so are there any questions on this part right here? All right, hold on here. Wait. Let me see here. Hold on. Can I scroll up slightly? Yes, Zachary. Well, what we can do, Matthew, what I can do, I mean, we're looking at an example, but I see you want to kind of have a example formally worked out. So what I can do is, how many would find it helpful if I formally worked out another example and put in the details I usually put in? Would you like me to do that and make a recording of that for you? Okay, Antonio would appreciate that. Okay, okay, and Andrea would. All right, let me make a note here. Hold on, I'll make a note to do that. Let's see. 7.5 recording. Okay. What I can do is make the recording, and I'll let you know when I've posted it under the course content folder. Okay, not a problem, not a problem. So, okay. So by the second translation theorem, then they come up with the they take the inverse Laplace transform, and they come up then with a solution. They come up with this solution. And I think you can actually really, you know how to use Laplace transforms. I mean, it's true they're leaving out some details, but I think you could fill in the details on this one. If I don't think you'd have a problem. And the problems in the homework for section 7.5, actually 3 out of the 4 problems have like help aids, watch it videos, so forth. So, but nevertheless, I will also work an example for you and get it posted. But okay, so do you see here? Do you see here how based on the what y of t is, then if we, the unit step function will equal 0 when t is between 0 and 2 pi, and it will equal 1 when t is greater than 2 pi. And so this is going to be your actual solution. This will be your actual solution. Okay, if you were to write it out, that would be your actual solution. And I think we'll focus just on part A from this problem. That'll be enough, so you get the general idea. But are there any let me just see here. I want to see if there's anything that I can add. They say, okay, sine of t minus 2 pi equals sine of t. That makes sense. The sine function is periodic. Sine function is periodic with a period of 2 pi, so sure. Are there any questions on what you see right there in front of you? How they got there based on what's above? Who's feeling good with that? Okay, excellent. All right, Andrea's good and Matthew's good. Okay, okay. So, what if we were to graph this? If we were to graph this y of t function, okay, if we were to graph it, what would it look like? Well, so the Mark, you don't understand how they got to this. Okay, hang on, one moment. No problem. We'll go to the blackboard here. Let me just write down the okay, one moment here. Let's see here. Share the whiteboard. Let me get the pen out here. Okay, so this example that we are looking at, example 1, they came up with this, that y of t was equal to cosine of t plus 4 times the sine of t minus 2 pi times this unit step function. Now the unit step function is going to equal 0, okay, just the unit step function. That equals 0 when t is between 0 and pi, and it equals 1 when t is greater than or equal to pi. Okay. Mark, are you good? Are you good with that? Okay. Very good. Well, then, so y of t would just equal, this is the sign here, would just equal the cosine of t when t is between 0 and pi, because this entire part will be gone, right? This entire term equals 0 because the unit step function equals 0 when t is between 0 and pi. But when t is greater than or equal to pi, you're going to have cosine of t plus 4 times the sine of t minus 2 pi. And that's when t is greater than or equal to 2 pi. Because then the unit step function equals 1. Zachary says, oh, I'm sorry, I have an error. Thank you. It should be pi. Hold on, let me just double check everything here. Wait. Oh, I left something out here. Hold on. I wrote it too quickly. It's 2 pi, right? It's 2 pi. Should have checked a little more carefully. Okay, so y of t equals cosine of t plus 4 times the sine of t minus 2 pi. Okay, and incidentally, the sine of t minus 2 pi, they just replace that with the sine of t because the sine's periodic with respect to 2 pi. So, okay, and let me just see here now. Got to dot my I's. I remember I took an algebra test in high school and I had 100% on it, but the professor took off a point because I didn't dot my I's on my sine functions. So all right, so let me just see here. All right, you're good, Mark. Excellent. And I guess here we just need the sine of t, right? On this part. Okay. So then, are there any questions on that before I go back to the example? Let's see, Zachary says, so cosine of t, hold on, cosine of t from, that's correct. That's correct, Zachary. So the reason we're getting two different functions here is because of this unit step function. It takes on 2 different values, depending on whether t is less than pi or greater than pi. That's why you have that split at t equals 2 pi. Yes, y of t equals cosine of t when t is greater than or equal to 0, Oh, sorry, and less than 2 pi. That's correct. That's correct. That's right. Okay, so are there any questions on this? Okay, how many found this helpful? I'm just sort of, I know Mark did, but I'm just kind of curious. How many of you found this helpful, just this little discussion here on this? Okay, excellent, excellent. Okay, okay. Next time I'll make sure I absolutely include that. Very good. Thank you, Kathia. So, okay, now we go back to the problem. And okay, and here, so now we've justified this function, why it is what it is. And if we look at the graph of this solution function, this is the graph here. Okay, so what this resembles, this is the graph of our solution to this differential equation. And the mass, you can see it's exhibiting from 0 to 2 pi, normal harmonic motion, no dampening. But then at t equals 2 pi, the mass is yeah. So from 0 to 2 pi, the mass is moving just normal harmonic motion. But then at t equals 2 pi, the mass there's a strike that occurs to the mass. And the influence of this impulse is to increase the amplitude of the vibration. So see the vibration, it goes greater. It goes greater. Okay, kind of like, I don't know, like maybe, I'm thinking like an earthquake. You know, maybe normal, you know, you got sort of normal behavior, and then, ooh, earthquake, and you get, you know, the ground, you know, shakes, and you got like, okay, you see where I'm coming from? Okay, so how many of you think this is a pretty cool application? Well, Antonio, it is wild. But, you know, in engineering, we have to be able to model certain phenomena. And now with this, with your understanding of this part of section 7.5, you'll be well prepared in the future. Are there any questions before I stop the recording? Okay, I'll stop the recording. Okay, very good.